in this lecture, I'm going to prove a hard theorem about classification of linear transformations. Of linear, of affine maps. Affine maps. So theorem is as follows. Every affine map is a composition of a linear map and a parallel transport. So this is a statement. Okay. So in coordinates, F will have a form. Let me write down as column xy goes to a matrix A, B, C, D times xy plus EF. So first I do a linear transformation and then I do a parallel transport. I can first do parallel transport and then a linear transformation, and one can always rewrite it as another linear, the same linear transformation but some other parallel transport. So order here doesn't matter much. So let me also rewrite it. If I write everything in rows, this will be AX plus BY plus E, comma CX plus dy plus f. So that's a very convenient way to think about it. Sorry, with AD minus BC not equal to 0. And you can just write down any formula like this. So for instance, you can take xy goes to, x plus y minus 1, comma x plus 3. That's an affine transformation. So literally just any linear forms, they are called. So any linear expressions in x, y, and 1 give you an affine transformation. So that's the theorem. And the theorem is rather hard, so let me kind of slowly prove it in this lecture. And the reason why it's hard is because we will have very few information to begin with. We know F is a bijection, and we know it sends lines to lines, as we already discussed. But how on earth would we come up with this A, B, C, D? Like, where would it all come from? Okay, so this is a proof. And I will do it in a couple of steps. So step 1. So parallel lines go to parallel lines. So I assume that I have F from R2 to R2, which is affine, and then I will prove certain properties. So parallel lines go to parallel lines. Affine transformations preserve this notion for lines to be parallel. And the proof of this step is really simple, is because if you take two lines L1, L2, and then you can take lines f of L1, f of L2. So the proposition from previous lecture guarantees that these lines actually are well defined. We know that every line bijectively goes to the other line. To compute it, you take any 2 points and see where they go. And so if there is any point of intersection of f of L1, f of L2, so then we know that f inverse of x by the previous proposition lies in L1 and L2, so L1 is not parallel to L2, and that is a proof. So basically follows from the previous proposition. Okay, so parallel lines go to parallel lines, and step 2 is that equal vectors go to equal vectors. So if you have, let me draw it, if you have a pair of vectors A, B, C, D, and you know that they are equal, so parallel, equal in length, and go in the same direction, then the statement is that they will go to certain vectors f of A, f of B, f of C, f of D, and the corresponding vectors will be also parallel, equal in length. So these were parallel and equal in length, and so these guys will be also parallel and equal in length. So the proof is as follows. So first assume, so if points A, B, C, D are not on the same line, then that's really easy, because we know that AB is parallel to CD, but also we know that the vectors are equal, so this is a parallelogram, so AC is parallel to BD. And so we know that this is a parallelogram, and so the same two conditions hold for points f of A, f of B, f of C, f of D, so we conclude that f of A, f of B, f of C, f of D are vertices of a parallelogram. I don't know how to denote it. So this guy. But then, of course, it means that vectors fa, fb equals vector fc, fd. So we get what we want. The only caveat here is that there was an assumption. So I said, assume ABCD are not on the same line. And what happens if points ABCD are on the same line? So this is AB, and then there is somewhere equal vector CD, but they lie on the same line. So we know that this line will go somewhere, and A will go to A1, B1, C1, D1, and Y actually these two things are the same. But the proof, which I'm not going to write, I just explain. So you just take any other vector parallel to it. So just take any other vector, I know x, y, or EF better. And then you know that this vector is equal to AB, and this vector is equal to CD, because AB and CD were equal. But then you know that EF will go to some other vector, and you know that this E1, F1 is equal to A1, B1, because we proved this proposition for in the case when vectors are not on the same line. And similarly, it's equal to C1, D1. And so you conclude that these two are equal as well. So in this way, it's easier to prove in the case when points are not on the same line, but the case on the same line follows. It's a simple geometric argument. So we know that equal vectors are mapped to equal vectors. So then we can just try to understand what our transformation does with vectors. So let me remind you what that means. So we have this origin. We know that f fixes the origin. And so what it means, i.e., for any two vectors v1, v2 in R2, so now I can ask what f does to a vector. So this is just, if always fixed, it is just where the end of this vector goes. But anyways, f of v1 plus v2 equals f of v1 plus v2. And that's first condition. And second condition, for any vector v in R2 and lambda in R, f of lambda v equals lambda f of v. And I just remind you, so if we prove these two properties, then we will just deduce. So then f of a point with coordinates x, y, if we take any coordinate system, will equal to a matrix A, B, C, D times x, y, because these are just where this vector goes, and this vector goes, and this vector goes. So this follows from what we discussed before. Okay, so let's prove this property. And there are two ways one can view it. So either you think of it as what f does to a vector v1, and then you can even not assume it sends origin to origin, because we know from previous part that basically what f does to a vector does not depend on the particular segment you take on the plane. Or you can think that f fixes O, and then you can think of it as just basically points. So how to prove it? So step 3, so step 3 is 1 is true. So 1 holds. So 1 is easy. And the reason, let's take OA and OB, and this will be V1, this will be V2. And then we know that, so we can draw a parallelogram, and this will be C, and this will be, of course, V1 plus V2. And then we know that, okay, O is fixed, so O goes to O, and then A goes to some A1, this is f of V1, and then this is maybe f of V2, and this is B1, and then there is a C1, and this is f of V1 plus f of V2. But then we know that line, so we know that line AC is parallel to OB, and then the line f of A, f of C is parallel to line OB. Actually, even vector is equal, so I don't know. But yeah, so let's just say, sorry, let's just say easier to say. Easier to say is just to notice that vector AC is equal to vector OB, and so this implies that vector A1C1 is equal to vector OB1. But that means, that means, of course, this implies that OC1 equals to OA1 plus OB1. This is just vector algebra. And so we see that if, and here we had OC equals to OA plus OB. So we see that this implies this, and so sum goes to sum. So f of V1 plus V2 equals f of V1 plus f of V2. And then we know that 0 goes to 0, and in general f is a bijection, so we know f of 0 vector goes to 0 vector. That's kind of trivial. And then also this implies that f of minus V1 plus f of V1 equals to 0 vector, and so f of minus V1 equals minus f of V1. So negative vector goes to negative vector. We are becoming close to this. Also, if you take f of n times v, this is of course f of v plus v equals f of v plus f of v n times. So this equals n f of v, and so one can actually take away not maybe arbitrary real number yet, but at least integer from here, positive integer. And also from here, that's true for negative integers. And also if one takes f of m over n times v, we know that if you apply it n times, you will get n times f of mv over nv, sorry, m over nv. And so f of m over nv equals to m over n f of v. So these two properties hold. This holds for any two vectors, and this holds for lambda being rational. Okay, so the question is how to pass from lambda being real to lambda being rational. And then if you assume that f is a continuous map in the sense of calculus of 2 dimensions, then it will immediately follow, just because you can take this lambda being any real number and construct a sequence of rational numbers converging to it and use continuity to deduce that if this is true, then this is true for any real number. And all the complexity of this theorem comes from the fact that we want to deduce it for arbitrary lambda without assuming f is continuous. So in particular, we'll get it as continuous, but a priori it's not obvious. And later I will give you an example where this kind of is wrong. If you do it not over real, but over complex numbers. Okay, so let's continue. Okay, let's summarize what we know. So we have this map F, and we know that it sends vectors to vectors, and we know that f of v1 plus v2 equals f of v1 plus f of v2, and we know that f of kv equals k f of v for k being rational. And the question is how to move to reals. So what about reals? Okay, let's deduce something else. So let's move on a little bit. So we know that a vector, we had these vectors OA and OB. Let's fix these two vectors going along certain axes. So this is just a general basis of our vector space, of the plane. And then we know that they go to OA1 and OB1, certain other vectors, and I don't want to draw them on the same picture just because it will confuse you a lot. So let me just draw it like that. So then I can take arbitrary vector here. So if I take f of OA times lambda, I know that this vector lambda times OA, it will go to a certain vector going along the line OA1, so it will be proportional to the vector OA1 with some coefficient of proportionality. So let me denote it by phi of lambda OA1. So there exists a function. So basically there exists function phi and psi, which will appear in a second, from real numbers to real numbers, which tells me that if I take a proportional to OA vector, how it will be proportional to OA1, and this phi of lambda is the coefficient. And similarly, if I take f of lambda OB, similarly I would denote by psi of lambda the corresponding function here. So this is another function. And the whole problem is that these functions are a priori some general functions. Let's see what properties do they have. So first observe that phi of lambda equals psi of lambda. So actually the functions are the same. And the reason is very simple, because if you take a pair of vectors lambda OA and lambda OB, you know that the lines going between the ends of this vector and this vectors are parallel. And so they go to vectors phi of lambda OA1, phi of lambda OA1, and psi of lambda OB1, and we know that this line is parallel to the line A1B1. And so what we deduce that the coefficient of proportionality, which is phi of lambda here, has to be equal to coefficient of proportionality, which is psi of lambda here. So these two lines, these lines are parallel, and thus their coefficients, this coefficients phi of lambda equals psi of lambda. Okay, so at least we know that f of the way how f rescales OA, how it changes the coefficient, is the same for OA and OB. Perfect. So now let's see how to proceed. So what properties does this phi have? So I will denote this by phi of lambda, this function. So now let me take arbitrary vector basically. So if I take f of any vector, say xoa plus yob, I know where it will go, because first I can say it goes to f of xoa plus f of yob, and then applying the previous statement, it goes to phi of x oa1 plus phi of y ob1. Now I can take f of lambda 1 plus lambda 2 OA, and on one hand it will equal to phi of lambda 1 plus lambda 2 OA, but on the other hand I can rewrite it as a sum f of lambda 1 OA plus lambda 2 of A, and so it be equal to f of lambda 1 OA plus f of lambda 2 OA, and so each of them can be rewritten as phi of lambda 1 OA plus phi of lambda 2 OA, and comparing the two we conclude, so for any lambda 1, lambda 2 in R, phi of lambda 1 plus lambda 2 equals phi of lambda 1 plus phi of lambda 2. So that's the first kind of result we can get. But then we can do something else. So if I take a vector, I can take a vector f of lambda 1 OA plus lambda 2 OB, and this will give me, of course, phi of lambda 1 OA plus OA1 plus phi of lambda 2 OB1. Again, applying linearity, and then this for the formula we have. But on the other hand, I can rewrite it saying that this is f. And then I can notice that this vector is parallel to the vector lambda 1 over lambda 2 OA plus OB. And since this vector will go to phi, similarly phi of lambda 1 over lambda 2 OA plus OB, and we know that these two vectors are parallel. Because these two vectors were parallel, they were just, one is rescaling of the other. But then the coefficients have to be proportional, and so we conclude that phi of lambda 1 over lambda 2 equals phi of lambda 1 over phi of lambda 2. And then one can just rewrite it as some x and some y, and this will be xy. And so we deduce that if I kind of rewrite it as lambda 1, lambda 2, I deduce that f of lambda 1 times lambda 2 equals f phi of lambda 1 times phi of lambda 2. So one should be slightly maybe careful here with zeros and everything, but one can easily deduce that phi equals to 0 only for zero vector from the fact that we have a bijective transformation. So basically we concluded that after our map phi has these two properties, and also I remind you that we also know that phi of lambda equals lambda for lambda in Q. And of course the only thing we need to show, so our goal is to see that phi of lambda equal lambda for lambda in R. And this is what we are going to show next. So from here we will deduce that this property holds for any k, and then we'll deduce that this f is a linear map, and then we'll deduce that it's given by the formula I wrote down before, and this will imply the result. So the only kind of remaining part is to show that if you have any function satisfying this condition and satisfying this condition and this condition, then this function is actually just constant. And if you assume that phi is continuous, then this will already imply that phi of lambda equal lambda for any lambda in R, and that's a simple exercise. But the interesting fact is that if you, in addition, assume that it sends product to product, then it will be constant without an assumption of continuity. Okay, that's the last step. So let me reformulate it again. So last step is as follows. So we take a function f from R to R such that, phi, from R to R such that, let me substitute lambda 1, lambda 2 as x and y, that's kind of more familiar. Phi of x plus y equals phi of x plus phi of y. Phi of xy equals phi of x, phi of y, and phi of x equal to x for x in Q, then phi of x is always equal to x for any x. So let me say briefly, such functions satisfying these three conditions are called, so these are called automorphisms. Morphisms of, in this case, R over Q, and in general they are very interesting. They form a group. The group is called the Galois group, and if you go to Algebra 3 you will study that. And this last step tells you that there is no such function from real numbers to real numbers. And if you take, instead of R, you will substitute it with complex numbers, as we will discuss very soon, phi of z sending z to z bar, the complex conjugate, so this a plus bi goes to a minus bi, satisfies all these properties. Property 1 to 3, this 1 to 3. And so there is something very special about real numbers here. If you take some other what's called fields, then it might not hold. So let me prove it. The proof is short, but I'm just emphasizing that it's quite a non-trivial statement. So proof is actually a few lines. So first, from 2 you deduce that phi of x squared is equal to phi of x squared, and so it's greater or equals than 0. So x is greater or equals than 0, then phi of x is greater or equals than 0. It sends non-negative numbers to non-negative numbers. And then, if you take x1 bigger than x2, then phi of x1 equals phi of x1 minus x2 plus x2 equals phi of x1 minus x2 plus phi of x2 by linearity, property 1, and this is greater than 0. And so you conclude, let me say greater or equal, that this is greater or equal than phi of x2. So your function preserves inequalities. And then it's easy to deduce that, so then phi of x equal to x. And the reason is because if you take a function and you know that it fixes all rational numbers, which are kind of dense here, so fixes all rational numbers, and you saw that it preserves inequalities, you can take arbitrary number x, which is a real number, and you know that it's basically so x being real, you know that it equals to, for instance, infimum of a set of all q in Q which are bigger than x. And then it's really easy to see that if phi preserves, sends rational numbers to rational numbers, basically the same, fixes rational numbers, and also preserves inequality, so then from here you just deduce that phi of x is also equal to the same infimum of the same set. And then you conclude that phi of x equal to x for any x in R. So the key here is that phi of x squared is greater or equal than 0, and of course this fails for complex numbers. So this ordering argument doesn't work. Anyways, so this is the conclusion, and so eventually we see that though we started just saying that an affine transformation is a transformation set, which is a bijection sending 3 points on the same line to 3 points on the same line, using very subtle algebra and properties of real numbers and properties of analysis and tons of other stuff, we concluded that all such transformations just have a form f of xy equal to ax plus by plus c, plus e, cx plus dy plus f for certain ad minus bc not equal to 0, so for certain matrix which is invertible. And basically we conclude that affine transformations have this very simple form, though we started with something very abstract. Okay, so in the next lecture I'm going to discuss the main properties of affine transformations which are useful in practice, how they rescale vectors and how they change areas, and I will show a couple of applications of affine transformations to geometry.